Good evening, everyone. And we're at another Thursday in our Math 185 class, and this is the halfway point. Okay, so I'm having some internet issues. This morning, apparently I was lecturing for an hour and wasn't broadcasting, and I didn't get the error message. So when it finally happened, I went back into class. They said, dude, you left at like 9:18 and now it's like 10:30. So it's like a big way. So I'll probably be periodically checking. Let's see here. Haven't looked at the test yet. I'll, be looking at them over the weekend. And there you go. So let's start with today's stuff. Share the screen. 3, 2, 1. Nope. Okay. Text mode. Up here. Should run the volumes all the way up. 185. Sequences and series. All right. Skyline, good. All right. So the ultimate goal here for us is we want to figure out in some way, shape, or form how our calculators compute like the square root of 5 or the sine of 3 degrees or the natural log of 3.02. All right, and this gets done instantly. You hit the button and boom. Okay, so obviously there's something going on in there, and that's kind of what we want to be doing. We want to try to figure out what's happening. Okay, so we're going to start with an 11.1 talking about sequences. Okay, now there's a few different definitions that we can use for sequences, okay? So one definition for us, a sequence, which we'll call maybe S, is an ordered list of numbers. Okay, now this list can be finite or it could be infinite. All right, so like, for example, we could have S equaling this list of numbers. How about 1, 1 over 2, 1 over 3, 1 over 4, and I stop at 1 over 10. Okay. Or I could have my sequence of numbers be given like this: 1, negative 1 over 4, 1 over 9, negative 1 over 16, 1 over 25. And this guy, I'm going to let go forever and ever. All right.
Are we talking about sequences like the Fibonacci sequence? That type of
Well,
thing?
we'll get there eventually, yeah. But we're just defining what a sequence is. Okay, it's just an ordered list of numbers. Okay, now some books, they define a sequence is a function f whose domain is the set of all counting numbers. Now, I don't like this definition for a few reasons. For one, and this probably is the only reason I need for this, 2, 3, 5, 7, 11, 13. What am I writing down?
All prime numbers.
Mm-hmm. Okay, so this is the list of the prime numbers. Now, there are a lot of unanswered questions about the prime numbers, but one question that has definitely been answered is, it has been proven that there is no polynomial function f such that f of n is going to give you the nth prime. Okay? There is no polynomial function. And for that matter, no rational function, and for that matter, a bunch of other stuff. Okay, now there are things that we can say about the primes. It's been proven after people went through Riemann's paper that the number of primes less than a given value n, pi of n, this is the counting of the primes, less than n, pi over n is approximately equal to n divided by the log of n. Okay, but that didn't help us with this. Anyway, that's the prime number theorem, by the way. Okay, so this is why I don't like this definition. Now, this list of primes is an ordered subset of the real numbers. You know, there's an x prime after 23, there's a next one. Okay. The Fibonacci sequence, as Brian was referring to earlier, is an example of something called a recursive sequence. All right. So a recursive sequence is going to be one where we get something like this: 1, 1, 2, 3, 5, 8, 13, 21, 44, 65. Okay, now this keeps going and going. Okay, so this is called the Fibonacci sequence. All right. Now we need to talk about what are we going to call these guys? Okay, so let's let S be a sequence. Okay. Now, if we have some kind of a formula F of n where the nth guy in the sequence which we will say A sub n is that guy, you find it by feeding it in there. Okay. Another thing that we're going to be doing quite a bit of is most of the time, not all of the time, but most of the time, we're going to start our counting with 0. Okay, now when we were back in pre-calculus doing this, guys, I stuck with what the pre-calculus book was doing, which started with A0. Then we started with A1. Okay, same author. I don't know why they do this, but there'll be some obvious reasons why we want to call the first guy A sub 0 as these next 3 weeks kind of move on. Okay, and so when this is the case, we will write S equaling the sequence. Okay, so when I have brackets around the A sub n thing, this means the whole sequence. As opposed to when I just say this, that's just going to be the nth guy. Okay. All right, so in the sequences that I wrote down earlier, like I think I wrote this one down, where it was 1, negative 1 over 4, 1 over 9, negative 1 over 16, 1 over 25, and this keeps going and going and going. Okay, then A sub n is going to be negative 1 to the n divided by n plus 1 squared. And this is going to start when n equals 0, 1, and 2. Okay. Now, if you don't want to start it at 0, you can start it at 1. And there are going to be more than one ways to do these things, guys. Just be wary of that. So I could report an in either one of these ways. Okay. For the Fibonacci sequence, where I had 1, 1, 2, 3, 5, 8, 13, 21, so on and so forth. The way that these get defined is A1 equals 1, A2 equals 1, and I'll stick with the starting at 1, so on, and says A1, because we're really not going to do much with Fibonacci. Okay, and then A sub n plus 2 is going to be equal to A sub n plus 1 plus A sub n, where n can start at 1. Okay, if you want to count these differently, you could say a sub n equals a n minus 2 plus a n minus 1. That's also a way we could do that. A3 is still going to be a1 plus a2. Okay. Now, there exists a formula for an. Okay, i.e., there is some formula talking about it one day, and he wrote it down. And I've been looking ever since for this on YouTube and stuff because I got interested. Okay, i.e., there is, was in the Lewis Center one day, and he wrote it, and I've been looking ever since for this on YouTube. Okay, I understand actually see in the feed by nature for some reason. If you count all of the petals in an altered daisy flower, it always in like a sunflower going this way and then going the other way. I guess I should have done that in a different color. That makes no sense to you now. What he'd somewhere, Fibonacci's original thought experiment. There was something about bunnies, okay, that he was coming up with these numbers. And the guy that was at maths, he's that English mathematician guy. He had a pretty good show on, we'll talk on the Fibonacci sequence. Okay, so for us, pretty much all of our sequences we're going to be able to find formulas for. But unfortunately, you know, the prime guys, I mean, if you found one that worked and the government would come and scoop you up and your family, and they'd never see you again. They'd put you to work national security, because always knowing a big prime that someone else doesn't know is important. So we'll talk about primes some more as we go along. Okay, so for this sequence, let's say a sub n, where the formula for a sub n is going to be given by n over n plus 1. We start writing down some of the guys. The first guy is going to be 0, 1/2, 2/3, 3 over 4, 4 over 5. Okay. So what does it look like is happening as n shoots off to infinity here? What do these numbers seem to be going to? What do you think?
Going to
You're gonna go straight to 1.
Going to 1, right? Okay, now we want to be able to say this without having to reinvent the wheel. Okay, so here's our definition. Okay, now we're going back to epsilon. So now for those of you, don't get all scared when I start proving stuff. Okay, there's going to be a bunch of proving going on in this chapter. What I want you to do when I'm doing that is just try to follow it. You know, take a screenshot later or stay after class, and then I'll just scroll up and down. But I want you to just try to follow these things, okay? It really helps separating ideas, I found. Trust me, I've been doing this for a while. Okay, so let's let this a sub n be a sequence in R. We're not going to be dealing with complex numbers until we get that back to Math 285, okay? So AN is going to be a sequence in R. So we say that the limit as n tends to infinity of AN is equal to L if for any epsilon that we want, there exists a big ass number B bigger than 0, such that if n is bigger than that big ass number, the difference between an and L can be made smaller than epsilon. Okay.
Could you repeat that again?
There it is right there. You can read it.
Okay.
Okay, now this is no different than we say
Hey, Bobby, what's the upside down A mean again? I'm sorry.
for all or for any.
And then what's the B next to that? The
That's-
one next to the such that or whatever that, or there exists.
There exists a big number B. See what I'm saying here is that if n gets bigger than this big ass number, these two things get really close to each other. They don't have to touch, but they get really close. Now this was the same as the definition as f of x, okay, equals L if for any epsilon bigger than 0, there exists a big number B bigger than 0, such that if x is bigger than this big ass number B, that implies that f of x minus L is less than epsilon. Okay, so it's the same definition. Now, I don't expect that you guys are all experts in proving with limits and stuff like that, okay? But if you thumb back to your Math 180 stuff later tonight, you'll see that it's just, you know, it is what it is. Okay, so let's suppose that we've got this sequence, we have a sequence AN, where AN is given by f of n. Okay. All right. Now,
Hey, Bobby, real
Yep.
quick. So, I'm sorry. If X is greater than B, what is that symbol after the X is greater than B?
implies.
Okay, what is that symbol supposed to look like? Is it supposed to look like that?
It's going to look like this. It looks like.
Oh, okay, it's an arrow. I got you.
Arrow. Okay. Now, if the function f is continuous on, let's say, this to this, let's say, not if, let's say, and this function is continuous on the positive interval. Okay, so let's see, what I'm going to try to show here is that the following statement. If the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of f of n equals L. And it seems like it should hold up, doesn't it? I mean, we're shooting off to infinity. Infinity is a big place way far out there. That'd be something. Okay, so let's get this going. Okay, now again, I'm going to do this slow. Try to follow it. Okay. Since we're given that the limit as x goes to infinity of f of x is equal to L for any epsilon bigger than 0, there exists a number b bigger than 0, such that if x is bigger than this big number b, then f of x minus the L is less than epsilon. Okay. Okay, so now, if we're now going to fix this epsilon, so this epsilon is now fixed. This epsilon above. Okay. All right, so, oh, by the way, I gotta fix this definition up here. There exists a big number b, a positive integer. Everybody go back and change that to that up there. Because technically, you know, we're not dealing in the continuum just yet. So, okay, now we're back down to here. Okay, so fix this epsilon above, okay? Now,
Can you go back up just a sec? I'm sorry. Oh, okay. Okay, thank you.
okay. So, and everybody, let's change this b to an n. I should have done n in the first place up there, but now it's all backwards. Okay. So, by the Archimedean property, and you know what the Archimedean property is, anyone? Or I tell you what it is?
Nope.
Okay, ready? Knock your socks off. You give me any real number, I can find an integer bigger than it. What do you think about them apples, huh? Okay, it's got to be said though at some point in time. Okay, now I'm not a logician, never studied logic. I don't know if that's an axiom or if that's actually can be proved. But anyway, by the Archimedean property, there exists a b, which is a number, and b is bigger than n. Okay? So, suppose that x is bigger, suppose, well, not x. Suppose n is bigger than this number b. Well, if it's bigger than that number b, it's bigger than n. So this says, according to this, anytime you feed something in that's bigger than n, f of it minus the L is less than epsilon, i.e. an minus L is less than epsilon, i.e. according to our definition, limit as n tends to infinity of an is now going to equal L. Okay, now why did we do all of that? What is that? What does that have to do with anything? Well, what it's going to allow us to do is not have to reinvent the wheel, okay? We have all of these limit laws that we developed back in Math 180, and we don't want to just throw them out and not use them anymore because we're dealing with n's and not x's. Okay, so like the advantage of this, like what would be the limit as n tends to infinity of 3n squared minus n plus 100 over 4n squared plus n minus 1? Somebody tell me what that limit is.
Infinity. No, it's negative 100. Oh, the
No.
Fuchs-Tran also said negative 100.
Is it 1?
3 over 4.
It's 3 over 4, guys.
Oh, just the first two numbers. Oh, I remember this.
Okay, now look. According to what I just proved, that's the same thing as if I did the limit as x goes to infinity of 3x squared minus x plus 100 divided by 4x squared plus x minus 1. Now that goes infinity over infinity, right? We would L'Hopital it and go x goes to infinity of 6x minus 1 over 8x plus 1, infinity over infinity, L'Hopital it again, limit as x tends to infinity of 6 over 8, and it's 3/4. Okay. Now, you wouldn't do this. Back when we were in pre-calculus, you just identify these guys. Oh, fuck. Undo. You just identify these guys. Okay. So like, for example, move the screen up a little bit. What's going to be the limit as n tends to infinity of, let's say, n over n plus 1?
And so do we do
1.
1?
1, right? That's what we suspected. We suspected these numbers, you know, they start at 1/2, 2/3, 3/4, 4/5, 5 over 6. They're getting closer and closer to 1, okay? Now, in Math 180, we had this discussion several times. Built into this is also the idea that the function itself, n over n plus 1, is not required to ever touch this guy. Occasionally, the limits do hit the thing. But see, if I tried to solve n over n plus 1 equals 1, that would leave me n equaling n plus 1. That leaves me with 0 equals 1, which is false. So there is no, there's no magic time where it's ever going to hit 1, but it's going to get arbitrarily close to it. Okay? So with these kind of guys, what would be the limit of this sequence of numbers as n goes to infinity? -1 to n to the n over n squared
-1.
as n goes to infinity.
-1, isn't it? And
Okay, let's see what's happening here. Negative, here's my sequence. -1, 1 over 4. -1 over 9, 1 over 16, negative 1 over 25. What's happening to these numbers?
Oh, they're
Circling 0.
They're going to 0. Okay. All right. So let's see. All right. So the moral to the story here is the following, the conclusion. Conclusion. All of our limit laws and results hold. What I mean by that is L'Hopital, the squeeze thing, theorem, anything else that we came up with, okay? So we don't have to go back and redo all of this stuff, okay? We've got this, all right? Okay, so let's see where I'm at now. Okay, so now limits that don't exist. Okay, now I want to compare these two things. The limit as n tends to infinity of n squared plus 1 over n versus the limit as n tends to infinity of negative 1 to the n. Okay, now I don't have much faith in you guys answering this question correctly, so I'll just answer it. What is the limit as n tends to infinity here? Well, the degree of the top is bigger than the degree of the bottom. And so we would
Oops,
say
says infinity. Oh.
plus infinity. Okay. And if we look at this limit, this does not exist. It's just flopping back and forth between 1 and negative 1. You can't get arbitrarily close to two separate numbers, okay? So both of these limits are going to be given the word diverge. They're both going to be limits that do not exist, okay? Now, I want you to compare this with the limit as x goes to 0 of 1 over x versus the limit as x goes to 0 of 1 over x squared. What we decided in Math 180 was that as you're going to 0, the right and left-hand limits don't match up. So I said, okay, so this limit doesn't exist. But this limit here, at least there's something to point at, okay? So what I want you to take away from this is that there's two flavors of diverging. There's this flavor, which is just kind of like nonsense, you know, snozberry punch, versus over here, where at least, you know, you can point to something, okay? All right, so that's the difference. All right, so blah, 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 and there we go. Okay, now we have arrived at kind of a, let's see, we're on here. Okay, so some results for us that are going to be useful. Okay, one result is if the limit as n tends to infinity of the absolute value of n equals 0, then the limit as n tends to infinity of an equals 0. Okay, now we use this all the time. Okay. Okay, and now again, let's do a little proof of this. So I'll pick an epsilon. Okay. Now, there exists an integer n bigger than 0, such that if n is bigger than this guy, the absolute value of an minus 0 is less than epsilon, right? That's just sticking stuff into the making pancakes thing, okay? Now this, Brian, when I write arrow that goes two different directions, that means
equals or
equivalent.
same
That
as.
means it's equivalent to.
Yeah.
So this would be equivalent to the absolute value of an less than epsilon, because 0 is 0, right? And no sense of having double absolute value signs. And if we insert the 0 back again, an minus 0 is less than epsilon. So what this says is that the limit as n tends to infinity of an is also equal to 0. Okay, now all of this action is taking place as long as n is bigger than that. Now, the first time I was learning this, it was a struggle. My calculus teachers did very little proving. They were just, here's the next formula, here's the next formula. Okay, and as a math major, I could have used a little bit of a kickstart. So if you have any questions about this proof, any of you that are interested, you can ask me like at the end of class and we can come and revisit it. Okay, there are some other results that you might remember. This is one that we're going to need. The limit as n tends to infinity of 1 plus 1 over n raised to the n. Does anybody know what that is?
Zero? Or Luke's saying it's 1.
He says it's 1. Okay, let's investigate. Okay, so let's let L be this limit. Okay, now logically, this might be an issue. You might say, hey, how do you even know it has a limit? Well, it'll get all fucked up if it didn't. Okay. So if L is this thing, now, and all of these numbers in here are all positive numbers, right? There's no negatives involved in here. So I can take the natural log of both sides. Okay. Now, last semester, what room were we in? 218 or 220? What was our Calc 1 class? It was on Monday, Wednesday, or Tuesday, Thursday?
Calc 1 was Monday, Wednesday. Every class I've had with you is Monday, Wednesday.
So it was Monday, Wednesday. So that was in room 218?
Yeah.
Upstairs, I don't remember.
Yeah,
Second
218. So I can remember us doing this. And this is the first massive result that we prove, that limits pass through continuous functions. Okay, so I can interchange limit and logarithm. Okay, Now that I proved. I didn't just say, hey, you know, take it from me, I'm telling you the truth here. The limit as x goes to any number of f of some other thing, let's say g of x, if f is continuous, the limit passes in and out of x when f is a continuous function. C0 is the symbol we use for a continuous function. Okay, so if we do some working with this now, again, I don't have to reprove all of the limit results because I just said that, hey, look, if it works here, it works here. Okay, so now as n tends to infinity, this is going to 0 in the middle, inside it, and that's going to infinity. Okay, so that's fishy. So when it's fishy, you got to play around with it. Okay, so the next thing I'm going to do is I'm going to bring the n down and put it in front of the logarithm, like so. Okay. And now when I look at it, it's infinity times 0. That's still fishy. Okay. So it's the limit as n goes off to infinity of the natural log of 1 plus 1 over n. And I'll move the n into 1 over n on the bottom. Now I get 0 over 0. So I can L'Hopital this thing. And for you new people, anytime I L'Hopital something, I write it over the equal sign. It's the limit as n tends to infinity. Okay, the top is going to be 1 over 1 plus 1 over n times the derivative of the inside, negative 1 over n squared. Should probably make that more legible. Negative 1 over n squared divided by negative 1 over n squared. And those two things are going to cancel each other to give the limit as n tends to infinity of 1 over 1 plus 1 over n. Okay, somebody tell me what that limit is as n tends to infinity.
Zero.
1.
A one.
One.
If I still say one. Yeah.
1. Okay, so was he right? Whoever said the answer was 1.
Fuchs said it was one. Yeah, he was right.
Said it was 1? Okay, was he right?
Yeah.
He was? No, he wasn't. Because what we just found was that the natural log of the limit L equals 1. See way back up here?
Okay. Not
Okay.
just the.
So that's the trick. Okay, so if the natural log of a number is 1, the number must be E. Okay, so I want you to try to remember this because it's going to show up. The limit as n tends to infinity of 1 plus 1 over n raised to the n is E. And the fact that E is bigger than 1 and positive is very, very important for things to come. Okay, now I'll give you guys another one, and you guys try to do this. The limit as n tends to infinity of the nth root of n. We're also going to need this one. Now, it turns out that this is 1. Okay, now you do it. Probably want to go n raised to the 1 over n power, call L the limit, and then do exactly what I did up here. And don't forget to undo that guy. Okay. So this first section, we end with a very important result. Okay. So the first result that we need to talk about, and Eduardo, this is kind of for you. Well, I have to do it anyway to prove this thing, but you should pay attention to this. The completeness, I'm writing how bad.
That made sense. Completeness.
The completeness, how do you spell completeness? Completeness?
Yeah.
E-N-E-S-S. You're almost there. Yep.
Completeness.
You wouldn't pronounce the E like that, but yeah, completeness. Yep.
It's probably
Another-
hurting the English teacher.
What?
It's
This
hurting
is
the English.
yet another dumb word in the English language.
I'm not gonna like
Completeness.
argue. No, English is a really stupid language, but completeness,
horrible.
we don't pronounce the second E.
We were all talking who were our favorite teachers for our kids, and they all of them except one had this woman at Woodland, Mrs. Ordaz. She was my favorite. She somehow figured out a way to teach them how to spell, and all three, the three younger ones, they all can spell because she had all kinds of tricks. And I think it's because she wasn't a native speaker. You know, she had to, man, she was really good. I wonder if Russian's worse than English. Probably not. Okay, well, here's what the completeness axiom, and I'll just refer to it as CA. Here's what the completeness axiom says. Okay, let's let S be a non-empty subset of the real numbers. Okay. If there exists a number B such that X is less than or equal to B for all X in S, then B, the set S, has a least upper bound.
Is that thing after the X? Is that the E that means such that?
Okay, so here, hold on.
A upside down A. If any X.
Okay, here we go. Let me read it out again.
Yeah.
Okay. So if
There exists.
there exists
Mm-hmm.
some B, which is a real number, such that X is less than or equal to B for all X in S.
Okay, that's what that little sign.
Element, yeah, in set theory, element of. Okay. Okay, so i.e. X is less than or equal to B for all X in S, and if B star is any upper bound of the set S, then B is less than or equal to B star. Okay, now I'm trying to write out in words what all of this is. Okay, so for example, let's let S be the set of all values of X such that X is sandwiched in between 0 and 1. Okay, so the interval 0, 1. Okay, now would you agree that every number in this set is less than 20?
Yes.
Now there's one number that is the lowest of all of these upper bounds. What number is it?
1.
So the least upper bound of the set S in this case is 1.
Oh.
Okay. Now, what is being said here is that in the proof, B is yet another real number. Okay, so is B star. Okay, now here's where it fails. This fails in the set of all rational numbers. Okay, if I let S be the set of all values X such that X squared is less than 2. Okay, so B equaling 2 is an upper bound, because if X squared is less than 2, what's going to happen is X is going to have to be between negative the square root of 2 and positive the square root of 2. Okay, now what would be the least upper bound on this set?
Shoot.
It's right here.
Oh, okay. It's
The
negative.
least
Square root
upper
of 2.
bound, the least upper bound of S is the square root of 2, right?
Oh, so it's not negative. It's not negative.
Well, no, we're just talking about the upper bound.
Oh, okay.
And this is not a rational number. Okay? So this completeness axiom, apparently it only works for the real numbers. And well, not just the real numbers, but there are systems of numbers, for example, the rational numbers, where this fails. Okay, and this was the example. Okay, now by using this completeness axiom, we're going to prove a very important result here. Theorem. Suppose, well, hold on, before I do theorem, we need a couple definitions here. Okay, so definition. We say a sequence AN is monotonic if it is increasing or decreasing. That's what it means to be monotone. All right. Being bounded means exactly what you think it means. Okay. So now, as a corollary to this result, by just changing things, the completeness axiom also holds for lower bounds. If S is a non-empty set and there exists a lower bound, let's say B, such that B is less than or equal to X for all X in S, then there exists a greatest lower bound, B for S, i.e. B is smaller than X for all X, and if X is bigger than B for all X in S, then B is bigger than or equal to B. So we call this B the greatest lower bound of S. Okay. Okay, so this is getting all mathy with this stuff. There's a few places in this chapter where we really need to get all mathy. Okay, so now here's our big, huge result. Okay. So let's suppose that we have a sequence AN, which is bounded and monotone. Okay. Then there exists a number L such that the limit as n tends to infinity of AN is equal to L. Okay. So a bounded sequence that's monotone is always going to have a limit. Okay. All right. So obviously the completeness axiom is going to have to come in here because we're going to have to produce a magic number L. And we have nowhere to go try to get it. You know, there's no cupboard for us. Okay, so here's the proof. All right. So let's suppose that the AN is increasing and AN is less than or equal to some upper bound B for all n. Okay. Well, by the completeness axiom, the sequence which is bounded above telemarketer. I used to always answer these calls. My wife would get so pissed. Say,
Would you screw with them for a while?
oh yeah.
I always do that.
Hi,
That's
hi,
fine.
Mr. Muir. Do you have a computer in your house? I don't know. Let me check. And I put the phone down. And then I come back like 5 minutes later. All right,
So,
what does it look like?
I
then-
feel, oh, go ahead, sorry.
I mean, I'm just on and on and on.
I feel bad about screwing with them. The ones I love to screw with are the people who they've like gotten the phone with my parents, the ones who like try to hack my parents' computer in those cases, like elderly people's computers. And they just spend like a long time talking about how you don't understand what a computer is, and because they make money if they can hack in or you buy them a gift card or whatever. I try to keep them on the phone for like 6 or 7 hours, just like doing other junk, so they can't get anybody else's stuff. They're normally, you know, not in the U.S., so it's kind of fun to screw with them.
Like
Do you guys ever get the call with the ching hong hong chong?
Oh yeah, I get that one almost every week. It's telling you that somebody, what is it? It's either that you received a package or somebody you know is in the hospital. I think there's 2 different ones.
Yeah.
But yeah, it's Chinese. Yeah, that one.
Well,
everybody gets that one.
last semester before we all went remote, in my math 285 class, I had these 2 girls who sat in the back and they wouldn't shut up. And they were talking and it was, that's what it sounded. They were, you know, he don't call. And then someone in the class goes, hey, don't they sound like those telemarketer calls you get? You know, and we're talking about them right there. And it didn't even phase them. They just kept running on.
Yeah.
Okay.
Yeah,
So
it's
by the
Chinese.
completeness axiom here, the set AN has a least upper bound L, i.e. AN is less than or equal to L for all n. Okay? Okay, now pick any epsilon we want. Positive. Doesn't matter to be small, okay? So L minus E is smaller than L, right? So this means L minus E cannot be and upper bound for the sequence AN. Okay. So as the sequence is moving along, it'll never exceed the number L, but at some point in time, the numbers have to exceed that. So there must exist some N, which is a counting number, such that if N is bigger than this N, the A sub N will be bigger than L minus epsilon. Right? Recall that the sequence AN is increasing. And so as soon as it gets past this L minus epsilon, it's not coming back. Okay? If I multiply, if I do some rearranging with this stuff, I've got AN is larger than L minus epsilon. So that's going to tell me that AN minus L is larger than negative epsilon. Okay, multiply both sides by -1 to get L minus AN is going to be less than positive epsilon. Okay. And remember that L is an upper bound. So L minus AN is positive. This is since L is bigger than or equal to AN for all N. And so certainly that would imply that negative epsilon, which is a negative number, that's smaller than 0. So that's L minus AN, and that's less than epsilon over here. Okay, no, not absolute value sign yet. Okay. Well, this is the equivalent of saying that L minus AN is less than epsilon, which is the same as saying that AN minus L is less than epsilon. Now, this is true whenever N is bigger than this number. This is the definition of what it means to be a limit. The limit is N tends to infinity of AN is equal to L. Okay. All right. So we're going to use this result a couple times in this chapter to get stuff. Occasionally, we have to go beyond the scope of the class to get this. All right. Any questions on this one?
So the first initial number is greater than the final number for the limit of N going to infinity as A sub N goes to the length.
Okay. All right. So 11.1 these are the sequences, okay? And he's got a whole bunch of exercises asking you what the limits are, do they exist? You know, just kind of get in there and do some of them. If you have problems, just make sure you're asking me. Okay, people will start asking me. Okay, now we'll start 11.2 and we'll come back to it later.
Wait, isn't this, sorry, at the beginning of class, I thought you said this was
11.1.
Oh, 11 point. Oh my goodness, man. It's been so long. I thought we were still in 10. Okay.
No, we
I
left
love it.
10. We finished 10 yesterday.
Okay. I thought we were finishing 10 today because you said we're going to need 4 weeks for 11. So,
Now he's got an interesting little example here. So this number 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over forever and ever. This thing is called a continued fraction. And it turns out it ends up equaling the square root of 2. Okay. Now these continued fractions, back in the 1800s, there was this mathematician from India named Ramanujan. There was a movie made about him not too long ago called The Man Who Knew Infinity. That was all about Ramanujan. And he did a lot of stuff with continued fractions. Okay. Now, in this exercise in my textbook, it looks like it's number 92. He's wanting you to, get in there and investigate it. Okay, so I don't think that's a waste of time. Matter of fact, I might do a little refresher course in this continued fraction Ramanujan stuff. Okay. All right, so 11.2. Now what we're going to do is switch gears and start talking about series. Okay. Okay, so let's see here. If we're given a sequence, A sub n, okay, the formal sum, finite or infinite, of this sequence is called a series. All right, now for most of us in the room that went through the traditional ways of getting here, this will be the third time that we look at this officially. We're supposed to look at it in intermediate algebra the first time, and then in either college algebra or pre-calculus, where we get a little more. And now up here, we're going to be using all of the results and really getting into it. Okay, so what we're talking about here is the series would be the sum, k equaling 0 up to infinity, of these AKs. So what it is A0 plus A1 plus A2 forever and ever and ever. We might have a finite series, sum k equaling, let's say, 2 to 7 of AK is going to be A2 plus A3, A4, A5, A6, A7, and it stops. Okay. Okay, now the main difference between these two series that I've written here is that This one, the second one, starts and stops. This one is infinite. We're going to find that when we have an infinitely long list of things that we're adding and subtracting up, sometimes the rules of algebra or the rules of arithmetic don't transfer into that. All right, so we're going to be seeing some kind of unusual examples here. Okay, so one way that we can decide if, you know, we have some like closed forms for some finite guys. Closed forms for a finite series. Like, for example, does anybody remember what the formula is when we add up the first integers and integers? 1 plus 2 plus all the way up to n. N times n plus 1 over 2. And that's the Carl Gauss, you know, figured that out when he was, you know, 5 years old or something like that. Okay. We also had another one. This is very important in finance. If we go k equaling 0 up to n of, let's say, r raised to the kth power, it's 1 minus r to the n plus first power divided by 1 minus r. Okay. Now, if we're given just some kind of a finite series, all the rules of arithmetic apply. There's nothing funny going on here. Okay. I can rearrange things. I can factor stuff. You know, I can do a lot of that. Okay. But when the list is infinite, things can get kind of weird. So I'll give you an example of this. What would be the sum as n starts at 0 and goes to infinity of -1 to the n? It's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. So somebody tell me what that equals.
0.
Yep, 0. But if I take this sum and I write it as 1 minus 1 minus 1 minus 1 minus 1 minus 1 minus 1. Now what I'm doing is, all I did is I factored the minus out and grouped them this way. Now what does this sum equal?
1.
And we can't have 0 equaling 1, right? At least not today. Okay, so there's obviously something going on here. Now, what I was trying to do here was use the associative property and in some way, shape, or form the distributive property. Okay, and I'm doing this on an infinitely long list. Okay, so what we're going to see is that sometimes a series will diverge like this one because it's just a bunch of nonsense. Sometimes the series will converge. Like, for example, just to show you that there exists one that works, n equaling 0 to infinity of the number 0. So that's 0 plus 0 plus 0 plus, what's that equal to? 0. Okay, so there is one that works. Now maybe that's kind of stupid. Okay. Well, you might remember this. If we go back to this guy, idiot dog, r to the k equaling 1 minus r to the n plus 1 over 1 minus r. Okay. If the absolute value of r is less than 1, the limit as n tends to infinity of r to the n plus 1 would equal 0. Just think about it. Take a fraction like 2/3 and continue squaring it on your calculator. Eventually, it'll go so small that it'll go to 0. Okay? So, with the magnitude of r less than 1, we can talk about the infinitely long series starting at 0 and going to infinity of r to the k. Now that's just going to be the limit as n tends to infinity of this finite guy, k equaling 1 to n of r to the k. And then if you just keep filling in what we're doing, it's going to be 1 minus r to the n plus 1 over 1 minus r. Our limit laws say we can go directly to the place where the limit is taking place, all over 1 minus r, and that's 1 over 1 minus r. Okay, so this is a result for us. Now I'll probably have to establish this again next week or something, but if r in magnitude is less than 1, the infinitely long sum from 0 to infinity of r to the n ends up being 1 over 1 minus r. And we have found our first infinite series thing adding up. Okay, so to decide whether or not a series is going to converge, we'll steal a page out of what we just did here. Okay, so here's our definition. Okay, so let's let an be an infinite sequence starting at wherever. Okay, we will let capital S sub n be the sum for k equaling 0 up to n of the AKs. So what that is, it's A0 plus A1 all the way up to AN. Okay, so SN, this is the third, there's so many different usages of SN, but SN is called the nth partial sum. Nth partial sum. Okay. Now, what we get here is a new sequence. This is the sequence of nth partial sums. So what we're going to say is if the limit as n tends to infinity of Sn equals S, something in R, then we will say that the series K equaling 0 to infinity of AK converges. And in fact, it actually is going to converge to S. Okay, and again, that's something that would require us to prove, but I think I've done enough of that stuff for today. Okay, so what we've done is we turn the problem into a slightly different problem. We take the convergence of an infinitely long sum and we turn it into a question about an infinitely long sequence. Okay. All right. Now, the truth of the matter is we're not really going to be all that interested in what these things converge to, just that they converge. Okay. So, like, for example, as soon as calculus was invented and people started thinking about these infinitely long sums, it was natural for them to start thinking about these things. The Knights Templar undoubtedly had this formula, 0 up to n of r to the k equaling 1 minus r to the n minus 1 over 1 minus r. It's been said that they had secret knowledge that they had gotten from the Essenes, which is, I guess, that would be the Islamic version of the badasses, you know, like they kind of got along with those dudes. And I think that the secret knowledge that they passed to them wasn't anything about God or magic or anything. I think it had all to do with money and equations and stuff, because the Templars, they went and started the world's first banking system with interest and all this stuff. And in order to compute interest and stuff like that, you need to not only have access to these kinds of formulas, you also have to have some kind of knowledge of logarithms. Okay. And for that matter, one could think, well, I mean, it doesn't take, you know, all that big of an imagination to think, if I keep increasing this n right here, this term, because r is smaller than 1, keeps getting smaller and smaller, you know. So I bet you that this result was probably known before people were openly talking about this new mathematics called the calculus. I mean, when I say talking about infinitely long sums, well, I know in the 1300s they were already doing it. Okay. So we'll be talking about that on a Monday. Okay, so we know that this thing converges. Converges by using calculus. Okay, but we don't know what it converges to. Now, what we're going to do with that, just so you can kind of see, I'm going to take the function f of x equaling 1 over x cubed, and then I'm going to put a bunch of rectangles underneath it. And we're going to, this is the integral test for next week. Okay. The integral from 1 to infinity of f of x, well, the sum k equaling 1 to infinity of 1 over k cubed would be adding up all of these rectangle areas. the width is going to be a 1. You know, this is a 1, 2, 3. Oh, jeez.
You have 2 pups?
Yeah. They
Both Yorkies?
No, one's kind of a poodle-ish.
Hmm.
Okay, but what we see here is that this is smaller than this integral, this improper integral. And that converges, okay? Less than infinity, that's what that means. Okay. Now, this is still an open problem in math. Nobody knows a closed form that I know of what it converges to. For us, later on, I'll actually work through this sum. I'll do exactly what Euler did, and we will show that this sum ends up being pi squared over 6. And his method gets all of the even exponents, but the odds are still a bit of an issue. Okay, so he talks about this geometric series a little bit. Some other types of converging series. If I was going to do the sum n equaling 1, well, let's do k equaling 1 to infinity of 1 over k squared plus k. Okay, so we'll let Sn be the nth partial sum. So k is going to go from 1 up to n. And then I'm going to factor this k plus 1. And then I'm so damn clever that I'm going to use partial fraction decomposition to break this apart into this. Okay. Come on, pen, right. 1 over k plus 1. Okay, now this is a finite sum, right? Okay, so it's going to be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1 over k minus 1 over k plus 1. So this is an example of something called telescoping. These things all cancel on the inside. The only thing that lives is this and this. So the Sn is the n, and then that's supposed to be n plus 1. 1 minus 1 over n plus 1. Okay, I'm going to go lock her up. Hold on a second. Okay, so anyways, this guy telescoped and he got to there. Now, the sum from 1 to infinity of 1 over the k times the k plus 1 is the limit as n tends to infinity of this Sn. And somebody tell me what that limit is.
It's the series of n.
What does this do as n tends to infinity?
Is it 1?
Mm-hmm. 1 minus 0, because this term goes to 0. So the answer is 1. Most of the time, we're not going to be able to do this. Know what it is. Most of the time. Okay. So let's start thinking about just some general ideas. Okay. So for infinite series, adding or removing a finite number of terms will not affect, is it affect or effect?
I think this one's effect because it will change things. But man, that's the difficult effect and effect. I always have to look up.
If it will not affect the convergence or divergence. So here's what I mean by this. If the sum k equaling 0 to infinity of a sub k diverges, then the sum k equaling n to infinity of the ak still diverges. If you take away a finite number of them, it's still going to diverge. Okay?
By the way, you're right. It was affect with an A.
It was?
Yeah. Sorry.
Okay. Okay. Now, the same thing could be, similar thing can be said about converging, you know. If the sum k equaling n to infinity of the ak converges, then the sum k equaling 0 to infinity ak converges. It'll converge to something different, but it's still going to converge. Okay. Now, the thing that's going to start driving you guys nuts is things going to 0, the sum versus the sequence. Okay. So, let's see here. What could we think might be a condition? Condition for convergence. Of a series. Okay, so let's suppose that I've got some infinite series AN and it's adding up to some L. Okay. So what must be true about the ANs? if this is going to work. Like,
Did we lose Bobby?
no, I'm here. I'm waiting for it.
Oh,
I'm asking a condition, like under what's a condition that we must have in order for this to happen? Like, for example, if all of these ANs are like e to the n, could this possibly add up to something? Because it would be 1 plus e squared. What's happening there? They're getting bigger and bigger and bigger, right? So if this is going to have a chance to converge, what might we say about the ANs?
It should get smaller.
Not only do they need to be smaller, they're going to all have to be smaller than 1, and they're going to continually have to get smaller. If I add up 1/2 to itself an infinite number of times, isn't that still infinity?
Yeah.
Okay, so in order to have a chance to converge, it seems like the limit of the things that we're adding up of the ANs must equal 0. Okay, so let's see if we can prove that. All right, so I've got my nth partial sum, and it's going to be A1 plus A2 plus, and then A sub n. Now, A sub n is equal to Sn minus Sn minus 1. Okay. Okay, now we're going to assume that this is a converging series. Okay. So that would mean that the limit as n tends to infinity of Sn exists, and it equals some s. Okay. And what would you think about the limit as n tends to infinity of Sn minus 1? Well, it's just 1 behind this guy, but we're going to infinity, right? So it's still going to be s. So the thing that we were interested in was what happens as n tends to infinity of this AN stuff. Well, it's the limit as n tends to infinity of Sn minus Sn minus 1. Our limit laws say that's s minus s, which is 0. Okay, so we have proven the following result. Okay, and this is called the criterion for convergence. If the sum of the ANs going to infinity converges, then the limit as n tends to infinity of the ANs must equal 0. Okay, now you got to be careful with this result, because the converse of this result is not true. Okay? Just because the things go to 0 doesn't mean the thing converges. Okay? So here is the counterexample. All right, so theorem or whatever, D or S semi 1300s is when he did this. And that's probably not how to spell his name. I have the book in my backpack. Where's it is though? That book didn't get stolen out of my truck. My good stuff with all the elliptic curve stuff got taken away though.
They're really
Okay.
picky robbers.
Yeah. They left a bunch of shit. Okay, so what D'Orsimi was able to establish is that this series 1 over n diverges. It adds to plus infinity. And it is what we call the harmonic series. Okay. Now,
Are we
the
talking
reason,
about similar to like guitar harmonics?
exactly what it is. Okay, the Greeks were all into this, especially like the Pythagoreans. So if you put your finger on a guitar string, guys, and Brian knows this, and you just at a random spot and don't push it all the way down, it's just going to go boop. But if you do it exactly halfway down the string and hit the string, it's going to make a noise. That's called a harmonic. Okay, and these occur at every one of these integers. Okay, 1/5 the length and so on. So that's why this thing's called the harmonic series. And if you get on the internet, watch this Smithsonian Institute thing with Eddie Van Halen talking about, you know, like how he's moving the nut around, he's getting harmonics everywhere and stuff. Okay, so now this, like I said, 1300s. Newton, Fermat, they don't, you know, they don't come around till the 1600s. So people were interested with infinite sums clear back to this far, probably even further. Okay. Okay. So what he does here is he starts looking at nth partial sums. So he looks at the first nth partial sum, S2, and it's going to be 1 plus 1 over 2. Okay. Then he looks at S4. He doesn't look at S3. He looks at S4. 1 plus 1/2 plus 1/3 plus 1/4. And he recognizes that that's bigger than 1 plus 1/2 plus 1/4 plus 1/4, right? Which is equal to 1 plus 2 over 2. Okay, now he looks at S8. Okay, 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and 1/8. And then he recognizes, okay, this is bigger than 1 plus 1/2 plus 1/4 plus 1/4 plus 4 1/8. And he sees that this is equal to 1 plus 3 over 2. Okay, so if you inductively do this, S sub 16, which is 2 to the 4th, is going to be bigger than 1 over 4 over 2. And in general, S sub 2 to the n is bigger than 1 plus n over 2. Okay. Now, because we're doing this with limits at infinity, the limit as n tends to infinity of Sn, that's going to be the same thing as the limit as n tends to infinity of S sub 2 to the n. Okay, there's just more guys. Okay, and this is larger than the limit as n tends to infinity of 1 plus n over 2. Okay, so somebody tell me what this limit is. as n tends to infinity? 1 plus n over 2.
Infinity.
Yep, it's infinity. Okay, so that means that the sum from n equaling 1 to infinity of 1 over n is unbounded. And so it diverges. Okay, so this is the thing that we want to remember. The harmonic series diverges. Okay. Now, D'Orsimi did this without any calculus. That proof that I have that I just offered up is pretty much what he did, pretty much, with, you know, a couple of different things. Okay, so this guy, the limit as n tended to infinity of the 1 over n equals 0, but the sum from 1 to infinity of 1 over n diverges. Okay, so see how this can be kind of confusing? So this is our thing that we're going to be making lots of comparisons to. 1 over n, the harmonic series, and how does that add up? Okay. All right, so what I'm going to do on Tuesday is basically I usually repeat everything I do in Math 185 when we get to this. And I say, okay, remember how this went? And then hopefully you guys will look at that. Now, it sounds like you guys are struggling with some limits. So I want you to get into that 11.1 and start knocking that rust off. Start doing those limits, okay? All right, let's give me a break here. I need to use the restroom and I gotta get my beer and let the dog out. And let's see who's still here.
What are we doing, Miller? This Miller today or Miller Lite?
Miller Lite and Ice, put it in here.
Miller Lite and Ice. Oh my God, it's horrible.
It's rehydrating, man. And I rode my e-bike around the back there.
You have the hydration in it, man.
You gotta have your hydration in your beer.
Yeah.
The worst sounding beer ever with ice in it. Ugh.
Hey, I've seen people turn those things into slushies and add all kinds of
Okay, so
stuff
I had a beer slushy in Japan. It was okay, like a Sapporo slushy or whatever.
Yeah.
It was all right. It's not like how I prefer it. I don't think it tastes that great, but it was an interesting thing to try.
I remember when I used to drink that stuff. It was, I think the last thing that I had that was a slushy was like a shrimp cocktail.
Oh, I've had those in like Vegas when I was like 21, but the sugar nowadays would like make me sick, so I can't have that anymore. Probably have a headache before I finish the drink. So.
Yeah, but it was like a slushy, but with shrimp in it. And you just, it was like a cocktail, but it was a slushy.
Sounds horrible, man. What? So you were drinking cocktail sauce, or what was the
cocktail sauce, or you dipped the shrimp? They were hanging off the side of the whatever the hell that was, and then you just dip them in there
into a drink that is cocktail sauce, and you drink this.
Yeah, it was like weird. It had onion, it had cilantro, it had everything.
It kind of sounds like a Bloody Mary.
Yeah.
Okay.
Yeah. But so you're just dipping it into like that slushy thing.
Oh man, it just sounds so weird.
It's so weird. It's like you could either suck on the straw, get the stuff in your mouth, and then eat the shrimp.
Ugh. What? Had beer. There you go, man. That's all that matters. I noticed after he was done talking, he talked about the harmonic series. It couldn't have been for guitar though. I mean, there was a harmonic series of guitar, but like in the 1300s, guitar didn't even exist. like
So
probably a
it was-
lute or
what's it called?
could have been a lute or a harp. I mean, I don't know. I think it would have had to be on a lute because the way that harmonics work, you're pressing down on the string to go like into the board. But the harp obviously doesn't have that because you're plucking the harp. So, but I mean, you can also do harmonics with piano too if you go inside where the strings are. So, just interesting. Harmonics are really cool. I don't know if you guys play guitar,
It's
but
really a harp, but like there is a part on the harp that if you hold the top part,
yeah.
it pinches the strings, and every third string is a third.
Oh, then maybe it is. Maybe you could do harmonics with. That's, no. I'm sure there's some pro out there who can do harmonics with a harp. But, I mean, I've seen so much crazy stuff now. Harmonics popular. Oh yeah, very popular with the harp. Okay, yeah, it seems like you're right. That's a totally. I'm wondering what instruments you can't. I mean, I doubt you could do harmonics with brass instruments.
You can probably do it on a what's it called? That bagpipe.
How he didn't mention anything.
You
I'm
squeeze
assuming
the
yes.
mic and you hold on the little puddle at the end of the neck.
On what instrument, Eduardo?
Well, it's a bagpipe.
Oh, bagpipe. Okay. It looks like. Oh, it looks like you can do harmonics with brass instruments. That's one I didn't expect. Hey, Bobby,
How would that?
What?
How would that work?
That's why I was, because we were talking about this. So guitars weren't invented in the 1300s. So they were talking about harmonics like way before guitars. So it was like lute or harp or a bunch of other stuff.
No, but there were strings.
Yeah, there's strings, lute, harp, all that stuff. Yeah.
Yeah, so they knew like.
But I was, me and Eduardo.
Did you know
were
"Sweet Child of Mine" is
Yeah.
all harmonics? Did you know that?
The beginning, right? That. Okay, I'll ask him. Hey, Bobby, Hal wants to know, one, if the test is on Tuesday, and will it be chapter 10? Yeah.
On Tuesday, well, it'll have some chapter 10 and some chapter 11 stuff. Now that we're in this environment, I can kind of mix questions in together. I've always been wanting to break up chapter 11 into 2 separate exams. And I was gonna think about doing it this summer because the chapter 8 exam, I only cover a couple sections.
Tuesday. I can never remember any riffs, man. I used to remember how to play like a bunch of songs, but I could barely even do the beginning of Stairway to Heaven anymore. I wish it was easier to like jam through Zoom because that'd be fun, but because of the lag, it doesn't work.
Okay, Sammy Hagar does a bunch of stuff with his band, with Jason Bonham.
He's local. He's like a local.
I think Michael Anthony lives in he has a house in that Cherry Lake place over there.
I know that I live like right across from Vanguard, and Sammy Hagar's like nephew, I randomly met him at our community hot tub area, and he was like telling me, "Oh, my uncle Sammy Hagar." I was like, "Oh, that's random." Yeah, it's that guy. So I think he's from Newport, man.
CC DeVille's son plays baseball at CDM.
Okay.
And so he's out there at the baseball game, or used to be anyway. Then Mike Ness, the dude from Social Distortion.
Yeah.
He has a place in that, you know what I'm talking about, that Cherry Lake.
Oh, I'm checking right now. Is it in Newport or which city?
So so are you familiar? So you know Santa Isabel.
Yeah, I live off Santa Isabel. I live off
so
of
if you got on Santa Isabel and drove towards the back bay to Irvine, right before you get to Irvine, there's a gate.
Oh, I know exactly what you're talking about. My buddy, I played lacrosse for Newport Harbor when I was younger, years and years and years ago. And we used to meet up, like one of the kids' parents had a house in there. So we'd go there for like club meetups or whatever.
I've never been in there.
It's really nice, man. I've literally been like twice, but it was like, whoa, I didn't know that existed. Because my where are you on? Are you near like 19th? Because my parents are on 19th.
No, I'm right near Kaiser, right near the elementary.
Oh, okay. Well, you probably see my parents' house. They have the big clock on 19th, the giant antique clock house with the not near the witch's house. So you know on Santa Ana they have the giant witch's
Santa Ana
house.
and 19th, the big airmail house.
Yeah, I always call it the witch's house because I had that cool spire. But
Oh,
yeah,
that's your
so my
grandparents?
parents' house. No, my parents' house is down that street. There's like a big antique Westminster clock off 19th.
Uh-huh.
And if you've been there for a long time, there was like a cannon and a flag. They removed that stuff. Anyways, that's their place. You'd probably notice it next time. It's a fairly large clock outside there
It's
that my dad installed. What?
It's near the museum on the other end.
No, it's East 19th Street.
Oh, okay.
Yeah, it's like very close to like where he lives. Like, because I live now, it's like my wife, we live over off of Vanguard Way, which is St. Isabel when you cross Newport Boulevard. But yeah.
I used to work with this guy, Mike Sinkeldam, when I had the job with Mercer. Like
okay.
that corporate job I had.
Yeah, you did for super short time, right?
Yeah, 15 months, I had a real job. And so Sinkeldam's wife, her sister is Michael Anthony's husband. So
Name sounds familiar.
Michael Anthony, the bass player for Van Halen, now with Sammy Hagar. So when Sammy left the band and they were trying to find singers, I'd be talking to Sinkeldam going, hey, tell him this, tell him this, tell him, yeah, giving him all these ideas. He didn't like any of my ideas. Though.
Yeah, dude, if you ever like search like the LA Times, that's the house I'm talking about for this Westminster clock because they got interviewed about it a few times. You would totally recognize it.
Oh yeah, I've lived here for over 20 years. I know the clock.
Oh, okay, yeah, that's where I grew up. So that's why I played for like Newport Harbor and stuff. But I went to a super small private school. So, but yeah, Kaiser's nice, man. It's a good area over there. It's crazy.
And now we have one at Ensign, and the rest are at Harbor.
Well, that's cool. They play lacrosse or no?
The boys play football.
Okay, I played that.
Avery's a tennis player, soccer player.
Okay. And lacrosse was fun, man. I don't know if they still play that. I mean, now they don't, but I don't know if they still played it before all of this. But
yeah, lacrosse is getting big.
It was, yeah. I mean, we used to play down in Newport. There was this famous player called Casey Powell brothers. Anyways, this was like early 2000s, and they kind of like helped start lacrosse in Southern California. And like one of them was a neighbor to the guy on the Newport Harbor lacrosse club thing. So like we would go down there and he'd like show us cool stuff. It was neat. I played club for 2 years. It's a fun sport.
Who's your coach?
Mark Monge, but he was I caught him on the last year, and then oh my goodness, dude, shorter dude was the second guy. This was 2000. I don't think so. This was 2004. It's a long time ago. I think it might be an actual school team now. It was a club team when I played.
Oh yeah, the best receiver from the football team.
Yeah.
He has a lacrosse scholarship to Duke.
Oh wow. Yeah, man.
Yeah.
Everybody knows them as the good guys of lacrosse. The Duke lacrosse team, historically well known. That's like the one lacrosse team where it's like, do you want people to know that you're going there? Because that was the one news scandal that, I mean, I know it's a good team, like in terms of like their ability. It's just like a really, just funny that that's going to be ingrained in everyone's mind permanently. Is like, oh, it's lacrosse, you don't want to go there. But yeah, man. What position do your sons play in football?
Trevor, he's a linebacker type guy.
Okay.
Defensive end. Tanner, I mean, he's going to be a freshman. So in youth football, he's the running back. And when I'm in charge of the defense, I have him at strong safety, but I have him flexed up.
Okay.
And but he's a natural strong safety is what he'll be
So
when he
he's-
gets to
He
Harvard.
doesn't have to do DB, huh? That was what I had to play because I wasn't good at playing. It's only good at running.
No, he'll be a strong safety.
Okay, it's a harder position.
I mean, depending on how big he gets, if he gets as big as his brothers, well, Trevor's bigger than me. They'll move him up to the line or, linebacker or something, but strong safety just seems to be his natural position.
Oh, what do you guys have any fun plans for the weekend or no?
Work and integral.
Oh, great. Eduardo, enough of that stuff. We're not in class anymore, okay?
It's traumatizing me lately. It's
12,
like,
okay? We're
I want to
done.
be able to do the problems that we had on the test faster than I did them.
Okay.
That's what's angering me. But the only way I can do them is just constantly just going back and seeing if I can pick up what I messed up and then just do them again.
Eduardo, if I hear
I've been doing them at work and
after
I got called
8:15,
out
I'm
at
gonna go
work the
crazy.
other day. My teacher, my general manager, he's like, "What are you doing on paper?" I'm like, "Integrals." It's like it's dead. There's nobody outside. Everything's fucking clean. And then I get home and I'm my giant computer at home doing spreadsheets, doing payroll and everything for the family business. And I'm still doing I'll get bored of one screen and then go back to doing half an integral and then go back to doing it and while it's loading.
Mm.
Good old HP computer that I have that hasn't died.
And Bobby's just gonna play Harmonics, Sweet Child of Mine all day. Do you have a recording setup, man? Harmonics, Sweet. Do you have a recording setup, man? What do you do? I'm always curious how people stay invested in playing when they're not writing or recording, because that's kind of the only reason why I play anything anymore. So.
Well, so the reason I was asking, it was named Todd.
Hmm.
So the head lacrosse coach now, his brother, who's the JV lacrosse coach, going to inherit the team. So
Okay.
he's one of my wife's friends. That's her boyfriend, and he's a drummer.
Oh, what band?
No band. He has a kit, and they got a garage. So he's wanting me to come over and set up. And I have a twin. But it's mostly just at night, just sitting on the couch watching TV, just playing,
I mean, you're probably way better at guitar than I am. I literally only pick them up when I have an idea, and I learn to play that idea, and I teach the idea to somebody who's better than I am. Then I have them play that idea, and then they record it. Because otherwise, I'm only sufficient at most instruments.
This thing's out of tune.
But now they have your whole setup. You could start recording whenever you want, man. You got all your stuff ready.
I still have in my garage my Tascam 4-track from.
I have one of those too. Are you talking about the blue one? Give me 1 second, man. I think I have exactly what you're talking about.